Hello, 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 1, 2, 3, hello.
Yeah, okay.
Professor Tewari distinguished lecture series. So this year, it's a privilege to have Professor Pertti Mattila. He's a well-known mathematician and a leading figure in geometric major theory, and he is going to give 4 one-hour lecture series on the application of Fourier transform on Hausdorff dimension. And he, of course, is a very celebrated mathematician around the world in this subject and has been invited as an ICM speaker in many awards. So with this, I would request Pertti.
Thank you. Well, thank you very much for the nice introduction. And yeah, so maybe 2 is too much. Okay, how is it now? Maybe, but it's not a very big. It's not a very big room, so maybe I don't need microphone. Do I need it? Maybe I manage without. Oh, let's try now. No, I take it away completely. Well, let me try without.
There is a lag somehow. We are hearing him and then the sound.
Right.
Okay. So thank you very much for Parasar and others for the invitation and organizing these lectures. It's a great pleasure and honor for me to be here. And I will talk about some geometric properties of very general sets, and I use Hausdorff measures, or rather, in particular, Hausdorff dimension to describe these properties. So S-dimensional Hausdorff measure, maybe everybody knows, but anyway I give the definition. So you have any set in Rn. So all my sets will be in Euclidean spaces, and this could be any kind of set. And then what I do, I cover it with small sets, and I try to minimize the the sum of the diameters to the power s of these for these coverings. So A is covered with some. If you prefer, you can take them to be balls. You don't get exactly the same measure, but you will get the same dimension. And I go to smaller and smaller sets, in particular if you want to define the length of a curve in this sense, that's what you get when you are applying this to some smooth or rectifiable curve. And then this is monotone in delta, and I can take limit in delta. And this is a Borel regular auto-measure in Rn. And Hausdorff dimension is then the parameter where this thing as a function of s drops from infinity to 0. So there is one borderline case. So the Hausdorff dimension of A is infimum of values s, so that Hausdorff measure is finite, or you can as well write infinity if you want it. It's the same infimum or supremum of S where it is positive. No, supremum of S where it is 0, and if you want, you can write finite, it's the same. So now I would like to ask some questions that if I know something about the Hausdorff dimension, what can I say about some other things related to this set, for example, about the projections of this set on lines. But using Hausdorff measure is usually quite convenient if you want to find upper bounds for the Hausdorff dimension, because then you can just pick a suitable covering and estimate this, and you can get upper bounds. Getting lower bounds is usually much more difficult, because then you have to use arbitrary coverings. And this becomes easier in many cases, in particular for proving theorems, when you use some modified definitions. So I assume that A is a Borel set, and all the sets that will appear will be Borel sets. You can also take them to be compact if you wish, because everything can be reduced to compact sets. So there is something called Frostman's lemma in 1930s. It was due to Otto Frostman, a Swedish complex analyst, who did this in connection of potential theory. And it says that Hausdorff measure is positive if and only if there is mu in MA, which means that mu is a Borel measure, and it's positive and finite, and it's supported by A. So there is a non-trivial Borel measure on A such that measures of balls, this is a closed ball with center x, radius r, are at most r to the power s for every x in Rn, and radius, positive radius. And this is not a very difficult to prove, but it changes this aspect that now you can, instead of looking at coverings, you can try to see what kind of measures you can put on your set. But it becomes often still much better if you kind of integrate this condition. So we are looking at the ratio mu bx r divided with r to the s, and this condition is boundedness of that ratio. But now I integrate it from 0 to infinity with respect to drr. And a little calculation shows that what you get is the potential. There is potential. So this is quite elementary. Well, maybe, I guess you need S here, but it doesn't matter. But so this relation changes this question to looking at measures for which values of S you can put a measure on this set with bounded potential.
Is that this mu can be up to the scalar multiple, it is unique, or can have several different measures?
You can have many different measures. No, they don't have to be unique at all. But it becomes still better if you integrate this also with respect to S. Then this is what is called S inertia of mu. So these names come from potential theory. If S is 1 and you are in R3, then this is just a Newtonian potential of the mass distribution mu. And one reason why this is often very useful is that now you can bring in Fourier transform. Because this IS mu is convolution Ks star mu d mu, just by definition. So Ks of x is norm of x to the power minus s, the Riesz kernel. And if you apply Fourier transform, you get Fourier transform of, and Blanchet's formula, you get Fourier transform of the convolution, which means that you get the Fourier transform of S times Fourier transform of mu, and from this you get Fourier transform of mu complex conjugate, so you get this squared. You have to be a little careful because Ks is not integrable function. It's not in any LP space. So what I am saying here then that, well, actually that is theory, you don't have to be so careful, but, well, maybe, yeah, you have to be a little. But then we know what the Fourier transform is. So this is just another Riesz kernel, norm of x to the power, well, with some constant. Norm of x to the power s minus n. And this is in terms of, in the distributional sense only. So you can write this as Csn integral norm of x to the power s minus n mu hat x absolute value squared dx. So this means that we can write the Hausdorff dimension in many ways. It's supremum of S, so that you can put mu on A which satisfies the growth condition. So this is just Frostman's lemma. And then you can write this in terms of inertia integrals. Oh, maybe I should write. So you ask for which values of S can you put this measure with finite inertia. And all this comes from these first considerations rather easily. And then the last formula gives me that this is supremum of S, so that there is mu on A, so that this integral norm of x to the power s minus n mu hat x absolute value squared dx is finite. So Fourier transform of mu at x, of course, is e to the minus 2 pi I x dot y d mu y. And this is a bounded function. So, so this thing is locally integrable. So the finiteness of this depends on how Fourier transform mu behaves at infinity. So this reduces the question of the Hausdorff dimension somehow to studying what kind of measures you can put on A with certain behavior at infinity. So these are somehow the basic tools which are used all the times in the kind of questions I am discussing, I will be discussing, and many others. Well, let's see now how one can use these to prove a classical theorem of Marstrand. So we look at projections. So I denote by PE the orthogonal projection from Rn to line TE, D is in R. And E is a unit vector. But I prefer to write it so that PE goes to R. So then PE is explicitly E dot x. To get it to go to the line, you should multiply this still with E, but that's unnecessary. So I want to ask what these projections do for various sets or general sets. So you could think of some example. For example, one of the simplest is if you take a product of two Cantor sets in the plane. So you start with a unit square, and then you take a square of side length d, and then you take in the corners squares of side length d squared, and you continue this d to the third and so on. This will converge to compact Cantor set CD, and you can easily show that Hausdorff dimension of this set is log 4 over log 1 over d. Well, why is it this? If I denote this by SD, then this simply means that 4 times d to the power SD is 1. But if this is 1, then also 4 to the k times d to the k power SD is also 1 for every k. Which means that in the definition, if you use those coverings, then the sums stay 1 all the time. And then to show that you cannot do better with any other coverings, you have to show that these are the best possible coverings. But you can also do it now by Frostman's lemma. You can start with the Lebesgue measure on this square, two-dimensional Lebesgue measure. Then you can redistribute it to these squares and keep going and check that growth condition is satisfied. So now I have this, and then if I want to project it to some lines, I take some line here, and I want to project it. So there are lots of these squares, and when you look at the projection, then there are lots of intervals, and it will not be very easy to see understand how big this projection on from these intervals. Because when you have a huge number of those squares, for general direction, these are rather irregularly distributed. They are overlapping and somewhere not overlapping and so on. But you can now prove something about what these projections do for this particular set and for general sets quite easily with these tools. So here is the theorem essentially due to Marstrand from 1957. Instead of projecting to lines, you can also project to m-dimensional planes in Rn, but I restrict now here to lines. And Marstrand's theorem says that if Hausdorff dimension, so A again is a Borel set. This Hausdorff dimension of A is at most 1, at most the same as the dimension of the line. Then the dimension is preserved. Projected sets have the same dimension as A for almost all unit vectors S, E. And you really need this almost all. You cannot, for example, say that except finitely many or except countably many or even except with a set with small Hausdorff dimension. There are some improvements for this, but essentially these exceptional sets can be uncountable sets, and this is in this sense a non-trivial result.
Maybe I have missed, so which set is almost every?
Sorry?
Maybe I have missed, so like set is for almost every unit vector. So which measure are you considering on Sn minus 1?
Well, the surface measure, which is the same as the n-1 dimensional Hausdorff measure. Just the surface measure on the sphere.
Can one also say something more about the dimension of the set in terms of the Hausdorff dimension?
Of the set?
Measure 0 set, where these things.
Yes, yeah, they are. So there are many such results on these exceptional sets, and those notes which are on the web page, I have listed some of them, and I will say something about them, maybe only during the last lecture. But you can, well, well, as I said before, the problem is to show that the Hausdorff dimension is at least dimension of A, because projection is Lipschitz. This inequality is always true. It can never be bigger. And the question is, can it often be smaller? Well, I can say now something about the exceptional sets. Robert Kaufman proved in the 60s that if you look at the set where this is less than this dimension, then that set has dimension at most dimension of F. So the set of exceptional E, in the sense that you look at the set where these projected sets have dimension less than dimension of A, has Hausdorff dimension at most dimension of E. That was Kaufman results from the 60s. But then there are more recent results and sharp results that you can ask that this is less than U. I can say also this. So this is then less than maximum of 2U minus dimension of A and 0. So do you understand what I mean? The set of unit vectors S, well, no, this is when n equals 2. When the set of those unit vectors where the dimension of the projection is less than some positive number U, that set has Hausdorff dimension at most this big. So when this becomes negative, then it is 0. And this is quite recently, this year, was proved by Ren and Wang. And it follows from the solution of the so-called Furstenberg problem, which I will discuss in the last lecture. So one can do more than this. Well, then the second part of Marstrand's theorem was and is that if dimension is bigger than 1, then of course we cannot have this because line has dimension 1. But then it is measure theoretically big. Then so this is Lebesgue measure. One-dimensional Lebesgue measure of projected set is positive for almost all in the sense of surface measure. Well, I would have talked about this for simplicity only on the plane, because these things are about the same in higher dimensions than in plane. But there is a third thing which was not done by Marstrand, which says that if the dimension of A is bigger than 2, then these projected sets have interior points. For almost all in the sense of surface measure, almost all directions. So in the plane, this doesn't say anything because there are no such sets in the plane. And in the plane, you cannot say anything because you can give an example of a set with full Lebesgue measure. So that's a set with Hausdorff dimension 2, so that all its projections have empty interior. You can build that rather easily if you know the existence of full line Kakeya sets or Bezigovich sets. But I don't go into that now. But but this is so this was proved by Falconer and O'Neill. I mean, this was not a question which was open for a long time because people couldn't solve it. It was open for a long time because people didn't think about it. The proof is very easy. So it was at the same time by Perez and Schlag, about 2000. So now I say something about the proofs.
May I ask something? Is it essential to assume that A is Fourier here?
Yes, yeah. Well, you can assume that it's an analytic set, a Susselin set. But you cannot assume that it's completely arbitrary. Well, I'm not quite sure. Maybe the example is only done with continuum hypothesis or something like this, but using something, set theoretic anomalies, you can build counterexamples for general sets. So that's why I always assume that everything is parallel.
So in the third result, so is this too sharp to have an interval contained in the...
Sorry?
Is too sharp for the...
Yeah, 2 is sharp. It follows from this plane example, then you can lift it to higher dimension. But if you project to m-dimensional planes, if you project to m-dimensional planes, then 2 here is replaced by 2m. And the same result is true, but then it is not known if this is sharp. So when you project to lines, sharp bound is known, but not for if you project to planes. So I say something about the proofs. Well, they are quite simple. So one follows from the fact that if I measure mu living on A, then I can project this measure to the projection of A. So So this is just a push forward. So I put here some measure, which is one of those measures which I use for those alternative definitions. I project here and I get measures here. And then when s is less than 1, then I can take the inertia integral of these projected measures. I integrate over the unit sphere, and then it's just a calculation, easy calculation to show that this is some constant times inertia integral of mu. And this is essentially all you need, because then Hausdorff dimension is, you start with number s which is less than the Hausdorff dimension, then you can find that this is finite, then for almost all these are finite, and from that you get the lower bound. So that's easy. Secondly, if you look at Marstrand's paper, the proofs are not so easy, but because he wanted to do things from the first principle. He was an ingenious mathematician who unfortunately died a few years ago, but he never, I don't know if he knew anything about Frostman's lemma and those things, but at least he didn't use it. So he started with definitions and basic properties of Hausdorff measures, and maybe his proofs are more illuminative than these fancier proofs, but they look more complicated. Well, secondly, now I start my assumption dimension of A is bigger than 1, so I put a measure mu on A such that this integral, which appears in the last of these alternative definitions, is finite. So this is integral with two Lebesgue measure over the plane, of course. Well, in Rn. And then again I project this measure, and now I look at the Fourier transform of this projected measure. At some real number d. You just check from the formula how Fourier transform is defined and how the image measure is defined. You can immediately see that this is Fourier transform of mu at dE. And then I take the Fourier transform of this projected measure at t, absolute value squared dt, integrate over r. And then I integrate over all directions. And I plug in this formula, so I get integral mu hat dE squared dt dE and I put 2 here so I can integrate from 0 to infinity and not over the whole line. So this is obviously integration of in polar coordinates of something, and the something that it is integral norm of x to the -1 mu hat x squared dx Well, there was no. No. Sorry, let's do this only in n equals 2. It is the same, we can say, but I have to be more careful with the exponents. So let's start again. So when I have this measure here, I have that this integral is finite when one inertia is finite, and I am in R2. And then this, by integration in polar continents, we have this equality. So this is finite. And this implies that for almost all unit vectors E, this Fourier transform of the projected measure is in L2 of R. But this, if you have a measure whose Fourier transform is in L2, then that measure must be absolutely continuous, essentially because Fourier transform is isometry in L2. So this measure has to come from an L2 function. So I simply write PE mu is in L2R, meaning that this measure is absolutely continuous and its density is an L2 function. But since these measures live on those projected sets, then this implies that these projected sets have to have positive measures when they support absolutely continuous measures or non-trivial functions. So that's the proof of 2. Then the proof of 1, I don't give it, but it is also simple. So you, instead of estimating the L2 norm, I estimate the L1 norm. But now not maybe everything. It's enough to estimate this integral from 0 to infinity. That will be enough because the rest will be finite anyway. And then, no, I don't have to say it because I don't do the details. So this is okay. So you show that this is finite. Using Cauchy-Schwarz inequality. By Cauchy-Schwarz, you get back to those integrals I had there, and then you show that this is finite when I2 mu is finite. So you can easily check this, and then you have that these Fourier transforms are integrable, and if you have a function whose Fourier transform is integrable, then that function is continuous by Fourier inversion formula. It's the same here, that we know only that it's a measure. It follows that this measure has to correspond to a continuous function. And if our projected sets support continuous functions, then they have to have interior points. So these were the methods that can be used to prove Marstrand's theorem, and then they, in various forms, can be used to prove many other things. So I will list some of the other methods which often come into the picture, which are more recent. And then I will say at least one case where one really needs much more. not only projections but also some other questions concerning these Hausdorff immersion type questions. Well, first, one can assume mu is a C-infinity function. Or let's say not always, but often. And it happens, the reason is that if you take a approximate identity to the function, C-infinity function with compact support in pole of radius epsilon with integral 1, then these convolutions are C-infinity and they converge to mu weakly. But in order to transform the properties from here to here, you need some kind of boundedness under this convergence. And if you, for example, you have LP norms bounded for p bigger than 1, b equals 1 is not good for anything in this respect. But for some p equals 1, usually p equals 2, then you can transform the properties to mu. So that's one thing one often does, that one moves to C-infinity functions. And then there is a discretization method which I think was started in this respect by Bourgain some a little more than 20 years ago, in connection of some projection type problems, and when he developed additive combinatorics in connection of Kakeya problems and things like that. So it means that in this case we assume that A is a union of balls of radius delta. And it is S-dimensional in this discrete sense, which first of all means that this K is about delta to the minus S, so that K times delta to the S is about 1. So that's somehow the covering condition relating to S-dimensionality. But you also need some kind of Frostman condition in this case. And it means that the number of indices I, so that these balls, let's call this ball BI intersected with some other ball BAR is bounded by R over delta to the power S. So this is not precise, but there is a method of getting to the discrete situation where this type of conditions appear, and then one can prove results in this discrete situation, so discrete analogs of those projection theorems or something like that, and then one can move back to the original situation. So this is often useful. And then some other methods are high-low decompositions. So you have a function and you write it as f low, f high, where f low has frequencies only in some bounded ball. F high has only big frequencies. And these functions can be defined so that f low is some, the Fourier transform of f low is something like eta times Fourier transform of f. So you localize the Fourier transform of f, and eta is is a smooth function which is something like characteristic function of some ball where C is suitably chosen constant. Then this part has Fourier transform living in a ball, and the other part has Fourier transform then living outside the ball, and that's often useful. Then there are decoupling inequalities in the sense that Bourgain and Demeter not so long ago have developed. I don't go into these now, but they somehow say that when you don't have orthogonality, you have some kind of replacement for that. Well, they are inequalities of the kind that you have some function, some of the functions, fj. You take the LP norm of this, and you would like to have the sum of the LP norms, which you could have at least if B is 2 and you have orthogonality. But you don't have this usually, so you want that this is somehow bounded by some of these LP norms. Squared and then square root. No, this is not a general inequality which is due to which is hold true for arbitrary functions. There are some very special assumptions, usually assumptions that you have some decomposition of some surface like a sphere in two parts, and then these functions have the property that Fourier transform is living on these different parts. Then you can prove something like this, and often they involve also something else here, not only that. But this is the type of thing which somehow replaces orthogonality. Well, that kind of methods are sometimes used and useful, and there are some others. But now I mentioned, so I say something about restricted families of projections. Restricted means that here I have considered projections to all lines, but maybe we only want to consider projections to some subfamily of lines. So there are many results that have recently been proven, and I have listed several of them in these notes. I take one now here. Which is due to this group in somehow centered at MIT and with Larry Good. This was, I think, Gunn, Guo, I don't, Good. Harris, Mallegue, and Wang. And these people have various results in other combinations and also with some other authors. But I take this one particular result now. In R3, so so instead of projecting to all lines, I take the unit sphere in R3, and then I take some curve on the sphere. Well, I should have set first this setting, so, but maybe I write it now below. So gamma is a curve on the unit sphere. is C2 and the span of gamma t, its derivative and its second derivative is R3. So this is a curvature condition which says that it cannot be any curve. So in particular, it cannot be this great circle here in the plane, because now I don't have projection theorem. Since this direction is orthogonal to this plane, this one-dimensional set projects to one point, and I cannot have analogues of Marstrand's projection theorem. But what I can take a circle which is somewhere here up, and that's okay, that satisfies these conditions. So for example, gamma t could be 1 over square root 2 cosine t sine t 1. That's okay. Then the theorem says exactly what Marstrand theorem says. Dimension of A, now we are projecting to so I take Pt to be the orthogonal projection from R3 to the orthogonal complement of gamma t. So I take these unit vectors, and then I take the orthogonal complement. I project those two planes. So these are projections to two planes. Then one is that the dimension of A is less than or equal to 2, then it is preserved. And then the second condition result is that if dimension of A is bigger than 2, then these projected sets have positive two-dimensional measure. And now their proof uses many of these ingredients I discussed here. They use discretization, they use this high-low decomposition, and they use decoupling. And it's quite difficult proof, but it is interesting because you can see many of these methods working there. Now I only say a little how this high-low could appear for projections. So these other results which I mentioned, they, for example, talk about projections to lines, and they have similar statements there. So if I have this discretization, I have these balls, or maybe I don't go that much even into details. I say it more simply. So, and we can think about this for this original Marstrand projection theorem. So we are projecting to lines in R3. And we have here some set which is S-dimensional. then we assume that these projections are some t-dimensional set. So A is here s-dimensional, and these projections here are t-dimensional. So then they are, this set A is contained, I assume that the whole set is in the unit disk, and then this set A is contained in some rectangles where this smaller side is delta and bigger side is 1. And then the Fourier transform of these things, so I take here some function psi. If this is R, this rectangle, then psi R looks like characteristic function of R, but it is a smooth function. Then the Fourier transform lives in a dual rectangle. If you have a function whose Fourier transform essentially lives in such a rectangle, which means that it's about 1 here and then it vanishes quite quickly when it goes out. Then the Fourier transform lives here is origin, and now this bigger side is 1 over delta, and this is 1. And psi R Fourier transform essentially lives here. So they are orthogonal to those. And now this happens for many E's. So I have some set of directions where I assume that the projection is E, and I have many such E's. And what I have to show that T has to be at least S. So I have this decomposition for many E's. Then I have many of these rectangles. Let's take another picture where I really make them small, narrow. So I have one direction, then I have another direction, and so on. And you can assume that you also discretize the set of directions you use. It's some finite set. And you can discretize it so that it's delta separated, where delta is this value you use for those radius of those balls. So any two directions have distance at least delta. So then all these rectangles coming from those different directions, so here is some E and here is some E prime, they intersect at the origin. But if you go away from origin a little bit, so this is delta, and this is 1, and this length is 1 over delta. And then you take this ball, the radius of this ball to be something like c over delta, where c is a positive small constant. Then the picture looks like this, roughly. That when these are delta separated by delta, these directions, they don't anymore intersect, at least not many of them intersect here outside this ball. So when you do this high-low decomposition and look at this high part, then the Fourier transform is living here. And then you estimate this integral f squared, where f is essentially the characteristic function of A. This is something, this decomposition can be done so that this high part dominates everything. It dominates low part. So this is essentially this. And for this you have some orthogonality coming from this kind of picture, because this is this high part is a sum of those things which live there, and there are Fourier transforms. The Fourier transforms lives here. You can go to Fourier transform here. And this will give you a lower bound delta to the minus s, and then some easy arguments will give you that's upper bound, lower bound delta to the minus t, and that will imply that s will be less than or equal to t. So this is only a very rough idea, but you can use this high-low decomposition for projections somehow, getting situation where these narrow things where some Fourier transforms live will be essentially disjoint outside some ball, and that you apply there. And what happens inside here, that for that you have to use some other argument, and I don't go into that. But I think my time is now up, so thank you for listening to this lecture. Sorry?
The Kaya, whose rectangles have fixed direction. I mean, they have all these R has same direction, right?
Sorry? I don't get.
These rectangles, Kaya, these rectangles have same direction.
This?
Yeah. The major axis of this rectangle.
Yeah.
All of these rectangles have the same direction.
Well, you fix a direction on your project, and then these rectangles will be in the orthogonal directions. But when you change this E, you look at many E's for which you project, then you change these directions. Yeah, you don't only look at one, but you look many.
Okay, so if there is no question, no other questions or comment, let's thank the speaker.
Sorry,
Is this only true for R3?
which?
For high dimension, it's not.
No, for higher dimensions.
Well, high and low is true for even the higher dimension.
No, high and low is, but